Welcome back. This is the second part of set of two presentations where I try to outline our new ideas on anisotropic inversion using isotropic modeling. In the first part, we introduced a new and exciting way to enable you to use pre-stack isotropic modeling and inversion in anisotropic conditions. Though the method can be extended to other types of anisotropy, and typically types of anisotropy where you can write your reflectivity equations in intercept, gradient, and curvature. The current implementation in the workbench is limited to VTI and HTI conditions. Here we will show some examples based on the technology which was outlined in the first presentation. Short overview, just two subjects. First I'll go through a feasibility study, and then I'll talk about some new tools and applications which we've put into our software to facilitate this workflow. So why do we want to do a feasibility study? Because we want to know beforehand whether the conditions you are trying to characterize in your reservoir are actually visible in the seismic, and you can actually get it out of the seismic data. So the feasibility here is that we'll make a model of elastic parameters and the Thomsen parameters, so VP, VS, and density, and the Thomsen parameters epsilon, delta, gamma, and the angle. And what we can do with that is we can calculate what we expect the anisotropy and the azimuth to be coming out of the inversion. So we can already tell what's going to come out of our seismic inversion. Then we can calculate the effective azimuth, calculate the effective elastic parameters they are azimuthally oriented. And with these, we can go through our elastic volume evaluator and calculate the anisotropy and the azimuth. And that should look a lot like what we expected. The next step is that we go through synthetic forward modeling and pre-stack inversions for every azimuth. And then again, after that, we can use that same elastic volume evaluator to calculate the anisotropy and the azimuth. So going through the workflow, there are three places where we can see what we're going to get out of the inversion. This is the model. There's a cross-section again of just the elastic parameters, P velocity, S velocity, density, and VP VS. And on top of that, I made my own impression, my artist impression of what I think the Thomsen parameters are. And note that these Thomsen parameters, they have no direct relationship with the elastic parameters. They're completely independent of the elastic parameters. So there's no encoding in there. You see that the azimuth here is constant per trace, but that's not a requirement for the technology. With this input data, we can calculate, because we know what the bias is going to be on our elastic parameters, we can calculate what the anisotropy is going to be, the expected anisotropy of the VPVS and the expected anisotropy of the density. So this is the azimuthal variation of the VPVS and the density coded into VPVS and the density anisotropy. So in the next step, we can calculate the effective elastic parameters as a function of azimuth. There are 6 azimuths here, and we're looking at the VPVS only. So there's a separate panel for every azimuth, and you can see that in the middle, the VPVS is changing. See, the blue is moving around as you go through the different azimuths. We can use our elastic volume evaluator to find out what the anisotropy and the angle azimuth is of the anisotropy. And here we can look at the VPVS anisotropy. The top is what we expected which would come out after using our input models, and the bottom is what we get out after calculating the effective VPVS for every azimuth and then analyzing the VPVS changes as a function of azimuth. Next step is to go through the synthetic seismic data generation. As you can see what we call a common offset, common angle gather, and you're going through every time you go through a CDP, you're going from near offset to far offset. See, on the near offsets there's very little variation in amplitude, and as you go to the further offsets, the amplitude as a function of azimuth is varying quite a lot. This is what you expect with HTI anisotropy. We take these synthetic data and go through inversion, and I'm not showing the separate panels here, but all the VPVS's are for every azimuth are after each other on one section view, but you can see the variation of the VPVS as you go from left to right. Then we can analyze the results. The top is what we expected to come out of the inversion. The bottom is what we actually get out of the inversion. And of course, this is a bit of a disappointment at first, until we realized that in the inversion we are of course using a wavelet in the forward modeling, and we're not encoding the low frequency model changes as a function of azimuth. So the inversion result is actually band limited, and we're only looking at a band limited version of the picture at the top. Looking at the wavelet which we used, it was a wavelet which was typical for land with a quite a high low frequency cutoff. The 6 dB is down is about 20 Hertz. So if we now put a low cut filter on the input data, which was in the previous slide, you can see that the picture changes quite a bit, and it looks quite a lot like what we are getting out of our inversion. So the lesson learned here is that the azimuthal analysis cannot reconstruct the low frequencies because they are not available in the seismic data, and you don't know what the low frequency model is in the first pass, so you're using isotropic model is a low frequency model in the inversion. So you really need the low frequencies in the seismic data. As this is a synthetic example, I can do that because I can change the wavelet and not put a 20 Hertz low frequency cutoff, but a 6 Hertz low frequency cutoff. And now you see applying a 6 Hertz low frequency cutoff on what we expected, it looks quite a lot like what we wanted to get out of the inversion. So a summary of the anisotropic inversion here. We have a method to quickly test the inversion sensitivity and directly use it on our input models. We can we can do our inversion, but in the first pass the azimuthal low frequency model is unknown, so we have to use the expected low frequency cutoff in the analysis. In the analysis of the final inversions, a branch is chosen, so polarity reversal in the analysis results in a 90-degree azimuth shift, and we preferably need broadband seismic data to reconstruct the low frequencies. So tools in our applications which we've put into the JSON package to support this workflow. We have some new applications. There's a SegWi loader for multidimensional trace and horizon data. So any trace header key can be used as an index or a horizon, and the horizons can be of the same dimensionality as the trace data. We have an anisotropic synthetics tool based on the Ruger reflectivity equations. We have anisotropic offset to angle converter. The ray tracing is using the velocities and the Thomsen parameters. And in the cartoon on the left you see that if you're looking at HTI data, there's, the rays are not straight in map view or in section view. So the group velocity and the phase velocity, they are not parallel to each other. So you need to know what the deviation is in both in azimuth and in angle due to your anisotropy. So we also have anisotropic elastic parameter calculation, where we can modify our isotropic elastic parameters using the Thomsen parameters to get our effective elastic parameters to be used in isotropic modeling and inversion. And we have an anisotropy and azimuth regression for azimuthal inversions, so that's our elastic volume evaluator. Some new tools for multidimensional data. We have a multidimensional section viewer. We can view the gather horizons as a map in a separate panel. So what you see here in the top panel is a seismic data, and we are extracting the values along the purple line here, this timeline, and those values are plotted as a function of azimuth in the lower panel. This is a nice tool to very quickly check whether you have any azimuthal variations in your seismic amplitudes. And of course, if you're in an area where you expect azimuthal variations, that's good. But on land data, you'll find very often that there is some azimuthal bias on your amplitudes. If you look at areas where you don't expect any azimuthal variations, you can check for that. We have rows and vector plots in MapView now, so you can look at your anisotropic inversion results and see in one picture what the directionality and the magnitude of the anisotropy is. We have a new file format for multidimensional trace and horizon data. We can create these multidimensional horizons from a single volume horizon. We can snap any gather, so that's any multidimensional horizon, to an event, either on the seismic or on the inversions, and we can extract the value at a horizon. So these are some of the new tools which are in the Jason Workbench, which you can use for your anisotropic analysis of your data. Thank you very much for your attention.